All right, guys, welcome back. Over the last many lectures, at least to the first part of the class, we've really sort of been focused not only on some of the really important basic thermodynamic and kinetic principles that undergird the chemistry of life and the physics of life. We've also been, in terms of the actual molecules we've been thinking about, we've really pretty much utterly been focused on proteins, right? And if you didn't already know, hopefully it's becoming obvious to you why proteins are so important, based on some of the lectures we've had, and more recently, the most recent set of lectures, their incredible importance to chemical catalysis in living systems, right? Their roles as enzymes, right? And we've spent a lot of time thinking about the basic principles over the last few lectures of how enzymes carry out catalysis, how we can measure that process, and now we're going to sort of turn around and apply some of these principles, not just some of the ideas of thermodynamics, but chemical kinetics and enzymology, to really begin understanding how the chemistry of life really works, right? So in essence, we're now going to move on from laying that groundwork. And I want to turn back to this question that I started the class out with, which was this idea that a key part of what all living organisms are doing is figuring out how to find the energy they need to exist, right? How do they extract energy from their environment in order to do the things they need to do as a living organism, move, make copies of themselves, and whatnot, right? Okay, so in sort of a big picture sense, then, what we're sort of really thinking about, right, is this idea of uh, taking the molecules that are available in the environment and breaking them down into sort of the smallest possible constituents, which for all the biomolecules we're going to be thinking about would be, water, carbon dioxide, and ammonia. And in the process, getting energy out of it, right? And this process of breakdown is, of course, known as catabolism, right? Where we take these larger molecules and then break them down in order to get energy. Now, of course, there's a paired process going in the direction where we utilize energy and these smaller components, and then build these molecules or build things back up to create the molecules we need for the all the functions that we would describe as life. And that is, of course, a process known as anabolism. Now, in the course of what we're going to be talking about for the rest of the class, we're mostly going to really be focusing on this process of catabolism. And that just comes down to an issue of limited time. And some of the deeper principles here about how enzymes do the things they need to do, how they're organized in order to get sequences of reactions to go. And some of the really key chemistry is highly shared between these two. Now, there are really important detailed differences, and I wish we had time to compare aspects of catabolism and anabolism in a more deep way, but we're just going to run out of time. I'm going to do a little bit of that in a couple of places just to give you a bit of a sense for it. But it's important to understand that almost all the sort of biochemical transitions we're going to be talking about from this point on are almost always paired. And even if we're focusing on catabolism, there's almost always an anabolic process that's going the other way to make stuff, right, that you need. All right, so turning back to this question of catalysis, or excuse me, extraction of energy, right? In the biggest possible picture sense of this, right, you can sort of define all the organisms that exist on this planet as falling into one of two categories, of course, right? There's, of course, the phototrophs, right, who use the energy of the sun, right, to create a whole set of molecules, principally carbohydrates, which we'll talk about later, as a storage medium, essentially for the radiant energy coming from the sun. They basically pack it into the molecular structure of carbohydrates, and those carbohydrates you can effectively think of as acting like batteries, right? They're a place where the potential energy derived from the radiant energy of the sun is used to synthesize molecular structures and store that energy, right? Okay. Then, of course, we have chemotrophs. which is anything that's basically not a phototroph. And chemotrophs, of course, get the energy they need to do all the things they need to do to live, principally by eating phototrophs, right? Or eating something that's eaten a phototroph, because their goal, right, is to get at those molecules um, which have stored this radiant energy from the sun and then extract that energy back out, right? Breaking these things back down by eating and digesting the molecules created by chemotrophs so that they can get the energy they need, energy and simpler components, right? They need. Okay, so there are some interesting exceptions to this basic idea, right? That you have phototrophs absorbing light from the sun, doing photosynthesis, making carbohydrates, and also fixing nitrogen, and then chemotrophs eating them or eating things that eat them. Um, and we have this nice little cycle of phototrophs and chemotrophs. And there are some interesting exceptions to this, um, uh, where you have entire ecosystems built around places where there is no radiant energy from the sun. For example, in deep thermal vents, volcanic thermal vents at the bottom of the ocean, where there is no radiant energy, and the chemotrophs, or there are chemotrophs that sit at the very bottom of those food pyramids that take the place of the phototrophs in our part of the biosphere, where they extract their energy from chemical reactions, um, um, which is sort of an interesting variation of this. So you can still make a very clean argument that ultimately that process still depends on the energy of the sun, or at least a previous sun. Those molecules that were created, or those atoms that were created, that allow these organisms to do this chemistry, or the thermal energy that's being supplied from the core of our planet, which was a consequence of gravitational collapse that made our sun, right? So in any event, I'm going to get hyper fine about it. The basic idea that you've got to have some set of organisms that can take energy from the environment, either thermal or radiant or chemical energy, create molecules that then the whole rest of the biosphere sits upon by extracting that potential energy from those molecular structures. Is sort of the core idea of this getting energy in order to power life, right? Okay, and you think about it, the amount of energy available in these molecular structures can be enormous, right? So one of the key molecules, of course, that sits at the center of this is glucose, right? And you can write out the simple chemical formula for glucose is just, C6, and we'll talk about the structure of glucose if you don't remember it, H12, right? O6, right? And the amount of energy available in chemical energy available in that molecular structure, you can evaluate, or you can measure through its just simple full chemical combustion, right? Which would be the addition of 6 oxygens, right? To then generate 6 CO2s and 6 waters, right? That would be converting that molecular structure and all those high potential electrons, the stored energy, into the lowest oxidation state for those carbons, that CO2 molecule, and water. And this combustion reaction, right? Like I said, there's a lot of energy available. The combustion-free energy, standard state, for that reaction is minus 2,870 kilojoules per mole, right? Yes, that's megajoules. A mole of glucose, right, is worth nearly 3 megajoules of energy, right? So that's great. There's a lot of energy there you could work with. You can do a lot of stuff with 3 megajoules of energy, right? A mole of glucose. Well, the question is, how do you get it, right? Now, what I've basically written out there, this is equivalent to like burning it, right? Or combusting it, right? That will certainly release all of that energy, right? But if you burn the glucose, you're just going to get all that energy out as one great big slug of heat, which is kind of useless unless you're cold, I guess. Or you have a steam engine on you, right? Then maybe you could do something with it. But the very best steam engines are really not that efficient, right? You get up to 30% or so efficiency and you're doing really, really, really good, right? Steam engines, any sort of combustion coupled device for using that free energy, using this free energy to do work is generally pretty doggone efficient. You waste a lot of that energy as heat, right? And that's a bad thing, right? In addition, biological organisms are not really well tuned to work at the temperatures and pressures necessary for a combustion engine. So biology is going to, or evolution has figured out a way to do the same basic thing instead of in a single big combusting step in a series of much smaller, more incremental steps that are going to allow for a whole set of really important things. And this sort of series of chemical reactions, which I sort of began introducing to you guys last time, is of course known as a pathway, right? And chemical pathways, as you hopefully remember, are a super important aspect of how biology works, right? Or biochemistry works. And they exist for a whole bunch of different reasons. Three of the really important ones, at least in the case of extraction of energy, is the fact the goal here is to extract out of this process a whole flow of high potential electrons. And if we can get them out, right, and they maintain their energetic potential, we can go on and do useful stuff with them, right? It's like the idea of having the power on in the socket in your wall. As long as the electric company is doing what it's supposed to, you've got an electrical field potential there, and the power supply coming into that wall socket plug stuff into it, and you can couple to that energetic potential and do work, right? Get useful stuff done, right? So that high potential flow of electrons, that's a big reason for running this chemical pathway rather than just blowing it completely out, is heat, right? And wasting most of that energy, right? There's a second reason for using chemical pathways to do this. Like I said, most organisms are not evolved to operate under the temperatures and pressures of a combustion engine, right? And so by using chemical pathways, you can get this process to go at completely reasonable temperatures and pressures, right? You can do the same basic overall process without the temperature going to, whatever, 2000 degrees or something like that, right? Third reason, right, and this is a biggie, right, is you can maximize, by using a series of more incremental steps, you can maximize the efficiency. Remember, big name of the game here is we want to get this energy back out so we can do useful stuff with it. If it all blows off, or most of it blows off as heat that we can't recover, then we're at a major selective disadvantage in terms of the competition for life. So by using a set of these incremental steps, you can think about this as almost a similar idea to the one you may have been exposed to in a class on basic thermodynamics, where the more irreversible a given process is, the more you lose some of that energy in, say, a simple steam engine to waste heat and to sort of losses to the second law, right? And by taking much, much smaller, more incremental steps, you can reduce that waste heat and you can improve the efficiency, right? And so this similar sort of idea here, by taking a set of individual, much, much smaller steps, biological organisms, by doing the same overall combustion process, going from CO2, going from glucose to CO2, you can actually then do this and extract the energy much more efficiently, right, with much less waste. Okay, now there's another really good reason for using chemical pathways for doing stuff. In addition to these ideas, there's another sort of big theme here, which is that in a lot of cases, when you want to drive some important chemical reaction, right? Let's just say we've got one, we're going to call it, we've got to turn A into B, right? Some reaction we have to get going, right? Because without it, we can't do some critical piece of metabolism. But that's not so favorable, right? This standard state of this transition is, I don't know, I'll make up something, plus 13 kilojoules per mole, right? So as we already know from talking about thermodynamics, that's just not going to happen spontaneously. But it just said we got to have it happen. Right? This is equivalent to my glucose 6-phosphate example, right? So another important aspect of chemical pathways is coupling unfavorable reactions like this that we have to have happen to favorable ones, right? And the obvious one here, of course, would be the hydrolysis of ATP. All right, so we just couple this reaction somehow using an enzyme to the hydrolysis of ATP, which of course has a favorable standard state free energy change of minus 31 kilojoules per mole, right? Which we can now, principle, write out that overall reaction is that it would just be A plus ATP, then goes to B plus ADP plus inorganic phosphate, giving us an overall free energy change now of minus 18 kilojoules per mole, right? So that's great. So by coupling this unfavorable but essential reaction to the favorable hydrolysis of ATP, we've made it happen. And we can write this out. So we call that equilibrium constant for AB, the one we really need to get going. We'll look at KEQ. And just to illustrate this, we'll call the overall coupled to ATP KEQ prime. So we know that KEQ, that equilibrium constant for that key A to B transition, would just be concentration of B, concentration of A, right? Which is now just going to be equal to E to the minus delta G naught prime over RT. You guys hopefully remember that, right? So that the equilibrium constant here is going to be somewhere in the range of about 1 times 10 to the minus 3. Like I said, not really going to happen, right? Okay. But that overall equilibrium constant, that KEQ prime, right, here, which is now going to be concentration of B, concentration of A, right, times concentration of, ADP times concentration of inorganic phosphate divided by the concentration of ATP. That now, with this, the free energy, that overall free energy here, right, that is now going to be, again, E to the minus delta G naught prime over RT, using the free energy for the overall reaction, is now going to be in the range of 2.7 times 10 to the 2, right? So if you look at this, right, that's an enhancement by coupling this reaction to the favorable hydrolysis of ATP. But that's like a 10 to the 5 order of magnitude enhancement, right? Which is great. It makes some sense why you would do this, right? You'd use that favorable free energy to drive this reaction, but it could actually be a little bit even better than that, right? Because if you think about it, the way I've sort of derived this here or been talking about it, this is assuming equilibrium, right? But we know living cells in general are not things that operate at equilibrium. True equilibrium usually means you're dead, right? So we can think about it. We can also think about it this way. We can say, well, how much more, or is there any more than that 10 to the 5th that cells can extract in terms of stimulating this unfavorable reaction? And the answer is, yeah, quite a bit, actually. So remember that KEQ prime, right, or KEQ star, right, that would just be equal to the KEQ, the equilibrium constant for the reaction on its own, which is unfavorable, times, right, the equilibrium constant for the hydrolysis of ATP, again, at equilibrium, right? And we know that the free energy at equilibrium for that coupled reaction, as we just talked about, would just be minus RT log of KEQ. But what if we're not at equilibrium, right? Living cells not at equilibrium. Well, that means, of course, we can write this out a somewhat different way. We know not at equilibrium, we would have some free energy under non-equilibrium conditions that's just equal to delta G naught prime for that process at equilibrium, which I just specified here, which has to be then adjusted for whatever the concentrations of stuff happen to be in the cellular context, right? Okay, we can write this out a slightly different way. We can say, okay, well, if that's true, then I could say delta G minus delta G naught prime equals RT log of Q. Well, I can write that different. I could say, well, that just means that the delta G, the difference between the standard state free energy and the free energy for this process under some set of conditions, raised to E divided by RT and raised to the exponential, is just going to be equal to Q, right? It has to be true. And I can write Q out a slightly different way. That has to just be equal to, right, we know, concentration of B over the concentration of A times the concentration of ADP, concentration of inorganic phosphate, divided by the concentration of ATP, right? So the whole question I'm sort of asking here is there any more that cellular conditions can give us? And so an easy way to ask that would be, well, what's the ratio of B to A, this unfavorable reaction, under cellular conditions? How much more of an enhancement could we get? Well, we can just rearrange this expression and get a feel for that, right? If I move this expression over here, I can write this out a different way and sort of illustrate this point. What that has to mean is that the concentration of B over A under cellular conditions is just going to be equal to E to the free energy difference under those conditions, right? E to the delta G divided by RT raised to exponent, right? Times concentration of ATP over the concentration of ADP concentration of inorganic phosphate under cellular conditions. Okay, so here's the trick, right? It turns out to be the case is that cells work very, very hard to maintain that ratio, that ATP to ADP ratio, at somewhere in the range of 500 molar to the -1, which means that under cellular conditions, all right, with cells working very hard to maintain this ratio of ATP to ADP, we get almost another 3 order of magnitude enhancement to the driving this unfavorable reaction from B to A, because cells maintain that, they don't maintain their ATP ADP reaction at equilibrium. They're working very hard to keep it balanced towards ATP, and that gives us this additional energetic kick to driving this reaction from A to B. Okay, next video, we're going to talk about why it is that ATP is such a good place to stick some of this energy.